I'm going to review a few things about Newton's third law, which is going to help us as we start talking about friction this week. So Newton's third law, as you recall, is for every action, there's an equal and opposite reaction. And what that means is that forces always come in pairs. And the pair of forces are the two equal and opposite forces that are acting on each of the two objects that are interacting. So in this case, we had seen this example before of the horse and the cart. The horse is pulling the cart forward, but the cart is pulling the horse backwards. And so if the horse pulls with 100 newtons, the cart pulls back on the horse with 100 newtons. And it creates this kind of situation that seems a little bit problematic, that the horse can't actually move itself forward because the cart keeps pulling back. If the horse pulls with 200 newtons, the cart pulls back with 200 newtons, and 300 and 300 and so on and so forth. Now, as we eventually got to in our conversation, we realized that the trick to this is what's going on with the horse's feet. And so if we look at the horse's feet and we consider how they are interacting with the ground itself, we see that there's actually another pair of forces, equal and opposite, the force between the horse and the ground. So in this case, the ground is acting upon the horse, pushing it forward, because the horse is acting upon the ground, pushing it backwards. Now again, we end up with this situation where the total sum of forces leads to a net force of 0. But the reason why this works is because if we block out the ground for a second and we just consider the system of the horse and the cart, we see how, yes, the horse and the cart have this pair of forces that balances out, but there's this unbalanced force on the system. And what that force allows to happen is the horse and the cart can accelerate forward. Now, meanwhile, if we look just at the ground, we realize that the ground also has an unbalanced force. And this seems a little bit strange when you look at this pairing of forces, because what it basically says is that, yes, the horse gets moved forward and the ground gets moved backwards. And that seems weird because we know the ground isn't really like a treadmill that we push beneath us. But in effect, it is, because whatever force you are propelled forward is going to be the same force that the ground is propelled backwards. But the trick of it is, if we recall Newton's second law showing the relationship between force and mass and acceleration, the Earth has a mass of 10 to the 24th kilograms versus the horse, which has something 10 to the second kilograms. So that force acting on the horse is going to cause a pretty significant, or at least a meaningful, acceleration, whereas that same force acting upon the massive Earth is going to lead to a meaningless amount of acceleration that's basically 0. So in this system, we see that because of this interaction with the ground, the horse and the cart are able to move forward. If we ignore the ground for a second and just look at this force, what this means is that the horse and the cart don't actually pull against each other in an unbalanced way. And so the horse and the cart never really move away from each other. And that actually makes complete sense because they're attached together by ropes or whatever. We know that if the horse moves forward, the cart's going to move with it. And if we look at this highly technical animation that I spent an embarrassing amount of time creating, we can see that as the horse is walking forward, it's able to pull the cart along with it. The cart, of course, has super frictionless wheels. They don't even spin. I wasn't going to try to animate that. So as this happens, the ground is being pushed to the left, the horse and the cart are moving forward, and that's because, again, when it comes to just the horse and the cart, we see this unbalanced force. Now, if we imagine a circumstance where the horse no longer has friction between itself and the ground, then we can see this kind of sad but hilarious circumstance where the horse, as it moves its feet just slide against the ground without actually pushing in any way, because what's actually happening when we look at the interaction between the horse's feet and the ground is that as the horse is pushing against the ground, this resistance, this frictional force is preventing the horse's feet from sliding, and so instead the horse is able to actually push itself forward. But if you remove that, then suddenly the horse's legs start to slide and nothing can happen. We don't have any net forward force, and so instead the horse just sort of sits here and the horse and the cart don't move. So as we talk about friction in the coming few days, we want you to keep in mind this idea of Newton's third law, because the balancing act between these two equal and opposite forces is super important to really understand where this frictional force comes into play. oftentimes I think we get trapped into thinking about friction as just this hindrance or this thing that slows stuff down. But in fact, if you stand up and walk across the room, it's only because friction that you're able to actually push the ground beneath you one way and propel yourself the other way. When you remove that frictional force and your feet simply slide, then you can't really do anything. So keep Newton's third law in mind as we start talking about friction, and what we're going to see is how the circumstance of what the materials are and the mass of the objects and gravity and everything else, how those lead to a calculatable amount of friction. And it has everything to do with, what the materials are. So the hoof of a horse versus the ground is going to be very different than the hoof of a horse versus a block of ice, or a piece of sandpaper and wood. Any two materials are going to have a very different situation when it comes to friction, and we'll get into the details of that next. So hope this helped. If you have questions, email me, please, and we will move forward with friction. Thanks.